Okay, the FRQ, this starts off here talking about tellurium. So tellurium on here, way down here. Okay, we can see it there in the front. So we're going to say, first off, is what is the electron configuration? So that we can do from the periodic table, and you can see it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p4. So you can see that it's in the fourth, fifth level down there, tellurium. 1, 2, 3, 1, 2, 3, 4. Yeah, fifth in the fifth period. Now, says a research paper suggests that the compound is covalent, because we're talking about it here. It's in that semi-metal range, so it kind of is maybe a metal or maybe a non-metal, and so they're saying, well, it's kind of maybe covalent. So do the Lewis dot structure for that. Well, you just say, well, because tellurium here is in the same column as oxygen and sulfur and all those guys, then we know that it has 6 valence electrons. Okay, so we give it 1. Well, if we're going to try to hook on 4 fluorines, that's going to take 4 of its valence electrons, and then that leaves 5 and 6 left over. So if we were going to do a sloppy version, it looks something like that. And Mr. Koo has a nice version. So we can see that that's steric number 5 with 1 valence electron, and steric number 5 looks something like this. Okay, but one of these is a lone pair. So what do we have left over? We have an atom here, 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 and here, and that, if we draw it kind of sideways, that's the seesaw. There's a lone pair up there. So that's the seesaw picture. Now, it's expected to be more or less polar than CF4. Well, carbon, family 4, it has 4 valence electrons. It's going to take those 4 valence electrons to hook on those 4 fluorines, so that's going to be tetrahedral. Now, even though, CF, that's going to be a nice polar bond, and TEF4, that's going to be a polar bond, is it more or less polar? Well, this is a non-polar molecule. CF4 is definitely non-polar because of its shape, so those 4 bond dipoles are going to cancel out, giving a non-polar molecule. But here, these are going to have a bond dipole going this way and this way. These two here, those are going to cancel, but there's nothing to cancel those two. So, this is going to have a net dipole, up and down. So, certainly, TEF4 is going to be more polar than CF4. Then we say, okay, well, explain why TEF4 is maybe more covalent compared to these. Well, SF4, if we were to look at that one, is going to be similar to the TE. I mean, it's the same family. Okay, lone pair is going to be seesaw. Okay, but that's definitely a molecular compound, and it's got a very low melting point, which makes sense. Okay, it's a little bit DDI. Okay, SEF4, same thing. Okay, it's a little bit higher up because SE, we can see from the periodic table here, SE, it has fewer electrons than the, it has more electrons than the sulfur. So because it has more electrons, a little bit stronger the London dispersion forces because it has more polarizable electron cloud. Okay, we'll jump down here to SNF4. Okay, SN, is way over here. Okay, here's tellurium. And so SN, that's actually over in the metal range for sure. So that's going to be ionic, and ionic is going to have a pretty large melting point. Okay, so these guys are really small. They're less than 1. This is pretty large. Tellurium, closer to these guys than they are to the ionic, and that's the kind of evidence that this TEF4 is on the covalent side. Okay, now we want to go back and say, okay, the light from a wavelength of 234 nanometers shines onto a piece of tellurium. The valence electrons are ejected with a kinetic energy. What's the binding energy of this electron? So what we're saying is, if we had a piece of metal and we shine, photons of light on there, we can eject the electrons, okay, photoelectrons, and they take some energy to eject those electrons, and the leftover energy is going to be their kinetic energy. So when we say the kinetic energy is this, that's leftover energy. energy that was not needed to get it to leave the surface, you know, the binding energy. So the more leftover energy, the greater the binding energy. So we can do E equals hc over lambda to take the lambda. So this guy here is, you know, the nanometers. That's the wavelength. You got to change that into meters. So times 10 to the minus 9th meters. And then hc, those are constants, and calculate so we can find out what is the energy of that photon of light that's going to hit. So that's this guy and this guy's in here. And then we say, well, the binding energy is the energy that goes in, okay, minus the leftover energy. So there's the energy that went in. Here is the leftover energy, the kinetic energy. So subtract those two, and that's where we get that value, and that is the binding energy, the energy it must have been held on to, the electron held into the tellurium metal. Now it says if we did the same thing with antimony, okay, and antimony is Sb versus Te, and it says would the antimony's electron leave with more or less speed than tellurium's? So you have to say, well, antimony is over here. It's going to have fewer protons, and if it's fewer protons, it's not going to be binding it as quite as tightly as tellurium. So if you put the same amount of energy in to antimony as you do to tellurium, well, then when that electron leaves, it's going to leave with more leftover energy since the binding energy is less. Okay, so it's going to leave with a greater speed. Okay. So more or less speed, okay, more speed than tellurium. Okay, the reduction potential, okay, for tellurium is this value here. A galvanic cell is made by doing tellurium in a 1 molar tellurium solution and tin in a 1 molar tin solution. Okay, the cell potential is found to be 0.78. So, after the cell runs, the mass of the tin electrode decreases, that's a big clue, while that of the tellurium electrode increases. So we have to decide, okay, is tellurium, this is reduction here, is tellurium going to do this reduction, or is it the reverse? That's our big clue. And we say that the tellurium electrode increases, the mass increases, and that means the ions are turning into the metal, so this is actually going to happen. Okay, so the tellurium is being reduced, okay, going from positive to 0, which means that it is the cathode. And that's the thinking. So because of the mass of the tellurium is increasing, it is being reduced, it's the cathode. And the same way the electrode, you know, the tin electrode is being decreased, which means that the tin, okay, metal, is turning into tin ions, okay, and so it is actually getting oxidized. So it is the anode, oxidation's anode. So determine the reduction potential of the tin. Okay, well, we know that tellurium, okay, 4 plus 4 electrons, that's pretty sloppy, plus 4 electrons turns into tellurium, and that must be a higher number than the tin, which picks up 2 electrons, becomes 10. You know, since this does happen as is and this is happening in reverse, then we know that this is a higher number than this, and this is 0.568 volts E0, and this guy here says that's going to be X, and when we're done, it's going to come out to be 0.708. That was the measured voltage of the cell. So we know that the cell is equal to the reduction potential, okay, plus the oxidation potential. And we know the reduction potential is the 0.568. And we know that this guy is 0.708. So when we do this, so we can find out that the X is going to be positive 0.14 volts. But that's not our answer, because that's the oxidation potential. That's this guy reversed. And so the actual number there is negative 0.14 volts. So little back and forth we have to be careful with. Okay, but that's how we do that answer. Now we're just going to do a little calculation. Okay, it says we have a 1.5 amp current for 30 minutes. What mass of TE is going to be formed? And we can see that this is written out really nicely. So we have the 30 minutes. Okay, we're going to change that to seconds. And then the fact that it's 1.5 amps, then that means 1.5 coulombs per second. That's how we translate. We use Faraday's constant, 96,500 coulombs per mole. Because this is TeNO3-4, we know that it takes 4 moles of electrons for every mole of tellurium, and then just the atomic mass of tellurium from the periodic table, and we get the answer 0.89 grams of tellurium. That's the whole question. Okay, good. Now we have some balloons. We have a balloon full of neon, okay, noble gas, SF4, sulfur hexafluoride, nitrogen, it looks like ethene gas, and chlorine. Now we can see that those are all going to be like nonpolar molecules, and they're all 1.5 liters at STP. So which pair has nearly the same density? Well, you know, they're all the same volume at STP, okay, so they're going to contain the same number of particles. So whichever is the heaviest particle, that will be the most dense, and the lightest particle least dense. We want some with the same density, so we need 2 of these that have about the same mass. So neon, checking the periodic table, that's going to weigh about 20. Okay, SF4, that's going to be huge. I'm not going to do it at 214s, that's going to be 28. C2H4, okay, well, no, Cl2, that's going to be about 71. C2, that's 24, 25, 6, 27, 28. Okay, so these two both weigh about 28. So N2 and C2H4, they're going to have about the same density. Okay, they're going to have the same number of particles, they have the same mass per mole of particles, so that's going to be the same density. B, which contains the greatest number of gas molecules? Well, Avogadro's hypothesis says, you know, if we have the same volume at the same temperature and pressure, they have equal numbers of molecules, and so, you know, these guys are all going to have the same number of gas molecules. Okay, which deviates most from ideal behavior? Okay, well, 2 things we're looking for deviating from ideal behavior is how much intermolecular forces do they have, and the other thing about ideal gases is they have no size. You know, they have no actual atomic volume or molecular volume. So these guys are all nonpolar molecules, so they're all going to be London dispersion forces. So the one with the most electrons, okay, they would have probably the strongest intermolecular forces, so it looks like SF6 is going to win on that one. And also SF6, that's a pretty big molecule compared to these other ones, so in both cases here it shows, you know, SF6 is going to be the atom that deviates most from ideal behavior. Okay, SF6. Okay, after 5 hours, some of the gases leak out of the balloons. Which balloons are expected to have the smallest volume? Okay, so you remember that, you know, rubber, you know, on there is just a whole bunch of different strands of stuff, and that the particles, you know, can escape through these little holes. Okay, and it's not so, you know, the holes are big compared to the particles. It's which ones are moving the fastest. So the fastest particles are going to escape the quickest. And fast, you know, the velocity has to do with their mass. So the smaller mass, okay, the greater the velocity, and so therefore the greater the escape, you know, rate of escape. So we're looking for whoever has the smallest mass of all these, and I think that's going to be neon. Neon is 20. Okay, so that's going to be the smallest mass. There it is, neon. Okay, combustion of butanone. It says the combustion of butanone is 72.11, oh, that's the molar mass, proceeds according to the following balanced equation, and there's the value. That's negative, which means it's giving off, and that makes sense because combustion heat is released. When a sample of unknown mass is reacted completely, okay, that much energy is released. What's the mass of the sample? Okay, so they're telling us the mass that's released when you burn a certain amount, so we want to find the grams. So we're going to start over here. Here's the mass. Okay, we know per mole is this many kilojoules per mole of reaction. And every mole of reaction, we get 2 moles of the butanone. And here's the mass of the butanone. So that gives us the mass of the butanone that actually got burned. That's pretty easy. Okay, what's the value of delta H of formation, okay, for butanone. We're given delta H of formations of CO2 and H2O, and okay, no, that's the two values right there. Okay, so we can kind of go back and remember what happens here, where you have hits of formation, so we can kind of do our shortcut, and that is going to be the products minus reactants. Okay, we don't have to worry about oxygen because heat of formation of oxygen is 0 because it's formation from its elements, and making oxygen from oxygen is not going to require any energy. So what we're going to have is that the delta H of the reaction is equal to 8 times the CO2 number. So 8 times the delta H of formation of CO2 plus 8 times the delta H of formation of H2O minus 2 times the delta H of formation of butanone and oxygen, which is going to be 0. So this is normal kind of stuff, except this is our unknown. That's our X. So we have a number for this. That's the negative 4890. We have 8 times this number, negative 393. We have 8 times this number minus 2 times X. And again, we don't care about the element. And then you just solve. And when you solve, you get 272.36 kilojoules per mole. The value of delta S is negative 465. At what temperature will this reaction become non-spontaneous? So we're saying here that the delta H, we saw that above here, okay, is negative 4890. So we get a negative delta H, and we said delta S, they're telling us that that's a negative number. Okay, so we say negative, negative, this is going to be spontaneous or be, thermodynamically favorable at low temperatures. And we're going to find out that that's not really the best way to say that. But, okay, there is going to be some cutoff, and below that cutoff, this will be spontaneous. Okay, so how do we do that? How do we find that cutoff temperature? Well, that would be where delta G is 0. We say that it's spontaneous when delta G is negative. It's non-spontaneous when delta G is positive. So what's the cutoff there? So delta G is 0. So we know that delta G is equal to delta H minus T delta S. So 0 equals delta H minus T delta S. So therefore delta H equals T delta S. And to solve for T then, so T is going to equal delta H over delta S. Now we're saying that it's low temperature, so it's going to be somewhere less than this temperature. So I'm saying this equal would be the cutoff, so I want something lower than what this is going to give us. Well, the one little thing here is that delta H is in kilojoules per mole and delta S is in joules per mole, so we have to make that change. And when we get done, then we get a temperature, okay, I'm sorry, at what temperature will this reaction become non-spontaneous? So I don't want to go lower than, I want to get, equal to and greater than this value. So when you do this, we find this is a really, really big number. Okay, and that's, kind of throw us off. But, we're just saying that at temperatures lower than this cutoff temperature, it will be spontaneous. So when will it be non-spontaneous? Starting at this temperature and anything higher, okay, that's when it's going to be spontaneous. So low temperature is a relative thing. It's lower than this temperature, it will be spontaneous. It'll be non-spontaneous at and higher than this huge number. And that is the practice test.